All right, welcome back to the third DWL workshop and its webinar series. Before we start with the webinar, I'd like to do a few acknowledgements, starting with the acknowledgement of the people of the Kulin Nation on whose land we are gathered here today, and I pay my respects to the elders past and present. Then, of course, I'd like to acknowledge the generous funding and support from the Australian National Fabrication Facility, ANFF, and its CEO, Jane Fitzpatrick. And of course, I also like to acknowledge my colleagues from the organizing committee for putting in all the hard work and making the webinar series and the workshop happen. And our sponsors, without them, this event would not have happened. So we're very glad that they support the direct light lithography community in Australia. And our sister meetings, conferences, workshops, starting with the thermal probe workshop in April this year in Switzerland, 3-beams meeting in Savannah, I believe, end of May, and of course the Mayville meeting for advanced electron beam lithography, which we took a lot of inspiration from in creating this workshop and webinar series. And this brings me to webinar 6, presented by Dr. Scott Lewis. And he asked me to keep his bio or his introduction very short. So I'm going to say two things. First, he has more than 15 years of experience in developing metal organic resist materials, which I guess we are very happy and glad that he agreed to come to us and present this webinar with the topic of what are the challenges for creating a next generation resist. And secondly, he already shared this information that he's very happy about this morning's Arsenal Champions League win. So we are we're even happier for you that this is the case. So they certainly will reach the next stage of the Champions League. So with that, I'll leave the introduction and hand over to you, Scott. Thank you again for agreeing to do the second webinar, and well, please share your screen, and the stage is yours.
Thank you very much, Mike. Could everybody hear me? Perfect. Okay, so I'm going to make my slide from the beginning. There we go. Okay, so we have a very interesting title here. Basically, what are the challenges creating the next generation resists technology? So essentially, as Michael says, that I've been working on this for 15 years now. I've been working with my close friend and colleague, Dr. Guy DeRose at Caltech. We're at Caltech together, as you can see in my affiliation. So what I'm going to do is basically talk about a recap that I did last, the webinar that I did last time, December, I believe that was. And then essentially we'll talk about what we've been doing over the last 15, 20 years. And I'm going to try and cram it all into a 2-hour if I can. But don't worry, it's not going to be like last time. There's going to be a little bit of maths, probably about this much, and the rest is just going to be pictures, so it won't be that intensive. So essentially, this is the contents. We did part 1 in December, so we just talked about scaling. I mean, we all know what that is, so I'll just run over that. We talked about electron scattering mechanics, so basically how electrons behave in materials, how are they different from primary electrons, secondary electrons, the daughters of secondary electrons, and how they damage the resist in order to form your patterns. We constructed a high energy and a low energy scattering model, so you should know all about that. We looked at single case materials, so I believe, if my memory serves me correctly, we did copper, gold, and silicon. I think zirconium would have been in there because it's got an atomic number halfway through, which is about 40 between gold and carbon, I guess. We looked at some design considerations. So I'm going to do that again, but I'm going to do it a little bit differently this time. And then we just talked about the case study between PMMA and ZEP that we all work with. I had some questions about that. I haven't responded to them, but I was going to respond after this meeting. So I just want the person who sent those questions in to say they haven't ignored them. I will get on and I'll get on to that. So essentially, today we're going to talk about part 2 that you can see. So we're going to talk about Auger generation, electron generation, and their scattering and what they are, how they affect the exposure, and what their contribution of the total exposure is. It's a very interesting mechanism, because depending on what materials you're using, that can be up to 50 or even about 50% of the exposure, which is interesting, depending on what energy regime you're interested in. So if you're interested in 100 kV, 30 kV, these sorts of things. So we'll run through some of that. And of course, we're interested in photoresists. So if you think about, from my position, that I can't get funding talking about I-line resists, deep UV resists, but I can get funding for EUV resists, because that's seen as the cutting edge technology seen today. So I'll talk to you a little bit about the actual absorption of these materials, or the elements of the periodic table. I think that Christoph Auger went through a little bit of that in the first presentation. So I'll go into a little bit more detail on that for you. We're talking about ligand design. So I'm going to do things by case study. So we're going to bring up like a particular molecule that we've designed, and then we will discuss it. And then what we will do is build up that fountain of knowledge and basically get to a cutting edge state of the art resist technology. So the foundation is the ligand, as in how do we bind these things together. And then in part 4, we've got our metal organics. We'll do that by case study, and then we will have a look. We'll go a little bit left, and we'll talk about how you direct semiconductors. So you can basically get resists that you irradiate with electron beam, and they reduce into semiconductors. So we can talk about that. So we talk about metal acetates and metal xanthates. We'll do that by case study. Then we can do direct metals. So we'll talk about metallic fluoride case studies. And then something that Guy and I have been working on for a while now, dual beam resists. So that means that we have a resist that can either be positive or a negative tone from the same material. That has a huge dry etch selectivity. And of course, we're going to talk about some dry etching case studies from these materials. So I'm going to get into this. So we're going to talk about, I'm going to move myself. I feel like I'm going to be doing that right the way through this, like I did last time. Yeah, so we're going to talk about Auger electron emission mechanics. Essentially, what is an Auger electron? So essentially, as you can see from the graphic in the top right-hand corner, we've got a primary electron, which is denoted as Pe. We talked about secondary electrons, which are SEs in this case. And then we've got something called an AE, which is an Auger emission. Okay, so essentially, we basically run our models in order to incorporate this. Okay, because as you can imagine, as I go around the periodic table, you essentially, as you go from, say, something like carbon all the way up to mercury or gold or bismuth, the amount of electrons in the outer shells, these shells get bigger and bigger. You can actually have more electrons in order to scatter from. Okay, so what this means is that you can actually generate more Augers at the higher atomic number species than at your lower. Okay, so that kind of seems obvious a little bit, but of course you can tailor these materials based on the energy of your electron beam. So, you know, if you're working with a 100 kilovolt tool, then you'd want to have a high Z material, something like a mercury-based material, or uranium-based, or obviously bismuth, something like that, which is rather safe. Uranium, I don't recommend. I'd work with that. But the uranyl is an interesting compound, very nice actually, but a bit toxic and lethal. But as long as you know how to handle it, you're all good. But of course, if you want to work with materials like indium, tin, antimony. Antimony is a bit toxic, so you probably want to stay away from that. But iodine, you want to work in the 30 kV regime. So the reason why is because the Augers, basically, depending on what species and what kind of tool that you have, you can basically get up to 50% of the exposure, which is contributed by Augers. And basically the mechanism works like this, really. So the electron comes in, it ionizes with the electrons in the outer shell. Because the electrons on the outer shell are easy to get to compared to the inner shell, the probability of striking these out are quite high. So essentially what happens is, like a diagram suggests, is that you can ionize and you can basically build like a vacancy. So the ionization of the electron can kick out an Auger electron, and it leaves a hole. So basically the electrons in the inner shells can fill that orbital. So essentially you can get like a secondary electron that we worked on last time, and an Auger. So you're actually getting, which is almost like an amplification point of view. So essentially this is the maths in order for you for it to strike out. This is what we put in our models, but essentially this map is probably the easiest way, this flow chart. So essentially what we do is we essentially understand if we've created, if we have a high energy electron that's created, we need to know its position, its energy and direction. So we check, has a Auger electron basically been determined? So basically, has it happened? We calculate the Auger probability, and that was given in the last slide. And then we generate the the Auger electron. Okay, so essentially this all these numbers. I'm going to move myself once again. So all these are the binding energies. Okay, so these are your K and your L's and your M's and your N's. And what this is you're going through. I've picked out some of the ones that I work with quite often. In fact, these are the ones I always work with. And essentially, what I need to know is what their binding energies are in order to work out, am I going to have enough energy to strike these out? And if not, will I have enough energy to strike these out? And then I can basically form a model that basically kicks these out. So essentially, this is what we do. So we need to work with this, and we get this data from the Lawrence Berkeley National Lab, and this is relatively available on their website. So yeah, pretty much that's where we're at. So essentially, we record the Auger when it happens. So when we kick the electron out from these binding energies, and then we look at the probability, and then has it happened? No. Then we just track the primary electron, and then we just carry on and go through it again. And if so, we track the Auger electron, and then we do it again. And essentially, that's how it works. All right, so we need to understand, for a photoresist, we need to understand the emission. So essentially, how the absorption of the resist can basically absorb the light. Okay, so EUV, I always think of it not as a wavelength but as an energy. So the wavelength is 13.4 nanometers, but I always think of it as 92 EV. So for me personally, I need to when I make a photoresist, I need to figure out, okay, so what's the cross section? So, we looked at the cross section of electrons last month, or whenever it was, and the cross section basically says, well, if you've got an electron, what's the probability of it colliding with matter, some atoms that are there? And this is basically the same thing. It's the photo absorption cross section, and we do this by elements. So as you can see that this is something I put together, but my good friend Yasin in Switzerland basically did this work a few years ago, and essentially I've just repeated it. So what we can see from here is that this energy, it will be different if you change this this energy. You can see that the low energy, so your carbon, your nitrogen, fluorine, oxygen they don't do very much. Okay, so that's down this end. What does the damage is here. So this is where it absorbs. So we've got 50, the atomic number of 50, 51, 52, 53, 54. You can see that these are very reactive. So this is basically 49. You talk about indium, tin, antimony, and iodine is the best. Xenon is basically a gas, so not a lot we can do about there. And of course, you can see that we've got the actinides over here, which are radioactive. So we want to stay away from those. As a physics exercise, that's why I work with uranyl based and neptunium-based chemistries. I was in a position where I was able to utilize that and understand what's going on. But this is, if you can see my cursor, this is where you want to be working. Okay, so this basically says that the probability of an interaction happening is very, very high indeed. So when Christoph Auger was talking about all the metal organic resists that are being made today in the very first, and he was talking about indium, this is the reason why, because this is very, very high. And yeah, this from a resist point of view, resist designer, we will use this. Okay, so we're going to go through some ligand design, but before that, we've got to go through some rules. I'm going to move myself again. We went through this last time, so I'll be brief if I can. These are the rules I always use. Okay, so we're interested in the atomic number. So that is the effective atomic number, because if you've got a molecule, you can't have an atomic number of a molecule because it's got many different atoms or many different elements. Different elements in it. So we basically say that's the effective atomic number. And essentially, if you think about the way that the elements essentially are, is that if you've got more electrons in the outer shells, then the more sensitive it will become, because the probability or the chances of interacting of an electron or a photon is going to be much higher. Okay, so essentially that once if you think from a photoresist point of view, let's say we take indium or tin in from an EUV point of view, the photon gets absorbed by the tin or the indium, and then it kicks out an electron. So that electron will ionize with some of the electrons in the outer shells, depending on what the rest of the molecule is. So if the atomic number is quite high, then the probability of ionizing it and generating secondary electrons, because secondary electrons do the damage, okay? And Augers, they do the damage as well, so let's not forget them. The sensitivity will go up. So that's great, because you want the dose or the sensitivity to be as high as possible and the dose to be as low as possible. Okay, so it's kind of counterintuitive, because you want to have the structures made in the quickest time. Okay, but of course, there is a trade-off. There's no such thing as a free lunch. So if your sensitivity goes up, it means you've got a lot of secondary electrons hanging around doing the damage. These secondary electrons, they're going to basically flood the immediate right area that you want to expose. And they need to be controlled, because if they're not controlled, your resolution goes down. So hence why we've got a red arrow going down and the sensitivity going up. Now, likewise, if your sensitivity is low, then your resolution goes up. And that's basically the way it works out. So essentially, that's where we're at with the atomic number. For the density, it's basically the same. So you can imagine if you've got like a gold, for instance. So the density of gold is 19.3 grams per centimeter cubed. What that means is that if you've got a gold atom and you've got another gold atom, or you've got something close to it, then the probability is going to be much, the gap between the two atoms is going to be a lot smaller. So if it's going to be a lot smaller, then the probability of the electron colliding with that, or the electrons in the outer shells, is going to be a lot higher. So it means you're able to ionize with it and strike out more secondary electrons. So in the shells of, let's say, gold, for instance, it has more electrons in the outer shells, meaning that you can strike out more. So you can basically, your sensitivity comes to you. But of course, then the resolution goes away from you. So it's a trade-off. Now with a molecular weight, it's the opposite. So if you've got this molecular weight is done from a molecule point of view. So if you've got a large molecule, let's say, and you've got the electron coming in, and you've got something that's massive, what happens is there's less material that governs the thickness of your film. So it means there's less scattering. So there's less scattering, there's less interaction. So it means there's your resolution goes up if your molecular weight is huge. And you're going to see something towards the back end of this presentation where we'll have a massive molecule to deal with. As I said, we're going to be going through these molecules, and they're just going to get more complicated as the presentation goes on. Now, if you've got a very small molecule, then you can fit more in the film. So it means there's more scattering, more ionization, more secondary electrons being made, and there you go. So you have that trade-off. And of course, we've got the ionization potential, and I mean that in terms of from electron scattering. So if your ionization is quite high, then your resolution is good. It becomes good, and if the ionization potential is low, then the resolution goes down. So these are. I'm going to be referring to these 4 parameters, and you're going to see firsthand how they change, why do they change, how do they change, and what is the outcome in terms of exposure. So when we talk about these 4 parameters or levers, think how many secondary electrons am I generating per unit area, and how many Augers am I generating as well. So of course, the higher these numbers, then the sensitivity is going to come to you. But if they're too high, then the resolution will go away. But of course, as always, there are other things to consider. You've got material solubility, so you need to spin the resist, or in my case, sublimate. I haven't spun a resist in years. Guy will tell you that. I essentially evaporate it. So I say evaporate, I mean sublimate, but essentially what we do, we heat it up in a vacuum, and essentially what happens is that it goes from the solid phase to the gas phase. Now, why would I do that? I do that because chemistry is a very, I spent over 10 years in a chemistry laboratory. Now, I'm not a chemist myself. If you asked me to go make some chemistry, I would run away from you. But I'm a physicist trapped in a chemistry laboratory. And one thing I noticed is when you make these molecules, they're filthy. Okay, so essentially, if you're making electronic materials, you need to make sure they're pure, okay, or chemically pure. That kind of means something different to a chemist, but we won't go there just yet. So what does this mean? So it means that once I sublime the resist, all the impurities are still left in the boat. So think of it as like if you evaporate some metal. So you have your substrate up here, you have your sublimation boat here, and then it basically forms beautiful mirrors. Okay, so the physics doesn't allow for impurities in the resist. So if you can imagine when you spin coat your resist, and sometimes you get comets coming out, and comets are always happen in the place where you want to write your resist. Guarantee it. But when you do it the way I do it, it forms beautiful films. So that's why I don't spin resists anymore. Other things to consider: atmospheric conditions. So I'm going to talk to you. I got an interesting slide to show you about what that really means. That is a killer. That is basically probably 70% of my work, because you can make the most beautiful molecule, and then the air gets at it, it attacks it, and it destroys it. And it does that on a wafer, and it's very annoying. And of course, we talked about secondary and Auger generation. So we basically got chemistry like alkenes. So I'm gonna talk to you about alkenes. I'll talk to you about amine technology and carbonyl chemistry. I'll talk to you about those. So these are the other things that I consider, and we will go through those now. Okay, so this slide looks a bit busy. I promise you that it's not. So if you can see my cursor, it's in the top left. So the way to read this is to basically follow it. So go down like so. Okay. So we go through these molecules, and I'll try and go through them one by one if I can. So essentially, we have ethane. This is a very simple molecule. Essentially, it's just a carbon. Where's my cursor? It's just a carbon-carbon bond. Very simple. You can imagine that this is very, very small. Has a low atomic number. The density is going to be fairly low, and you can see there is 1.28 grams per centimeter cubed, and the ionization potential is about 86. Okay, so you can see that where this forms on the secondary electron generation, right? So as you notice, they all kind of follow the same curve. Okay. And likewise, the same for the Augers as well. So this is a busy slide. So what I've done, I've basically made a slab of this in my model. So it's called Excalibur. I've inserted 1 million electrons, and then I've looked at how many secondary electrons are being generated. Okay, and I've looked at this because I work in this regime down here. So 10 kV to 30 kV. And I also work at 50 kV I also work at 100 kV. So I have to go right across because, you know, when I bond metals, and I'll show you how we do that, metals to these things, I need to know what regime or what exposure. I don't know why that's just happening. Sorry about that. So I need to know what exposure electron energy I need to use. Okay. So as you can see that as the molecule gets bulkier, okay, and bigger, you know, this basically comes, the amount of secondary electrons basically decreases. So it's quite difficult to tell down here, but it follows the same trend as this. So usually I just look at this, and if I want individual values, I'll basically just look for them. And essentially, this is these are the sorts of molecules that we're looking at. So these are what we call inactive. Okay. So they're kind of passive molecules, really, apart from this isonicotinic acid, and I can talk to you a bit about that in a minute. But as we go through, you can see that as you know, you've got these tails, the molecule is getting bigger, so it means that the amount of secondary electrons you're generating is getting lower and lower. So this is the ligand design. What I can tell you is for high resolution and and basically the trade-off between sensitivity and resolution is iperbolic acid. You'll see me work with this a lot, and this trifluoroacetic acid. Okay. These two are what interests me at the present moment in time. The acetic acid is quite, it gives you great resolution, but it's very hard to work with. And we'll talk about that in a bit. So essentially what happens here is if I put some metal on these oxygens, essentially when I hit it with an electron beam or I hit it with an EUV, this kind of acts like a lightning rod. So you can imagine the secondary electrons that get generated from here basically just go down here. It follows the carbon line, okay, until they get to ground. So on every collision, this thing's getting destroyed and basically getting obliterated. And then this reduces into like a metal oxide or a metal oxyfluoride in these cases. Okay, so what's happening now is that as I'm moving away, you can see I've got chlorine here, I've got fluorines. So what's happening there is that you've got, excuse me, so these are basically got higher density than carbon. Not by a lot, if I'm honest, but they will bring the sensitivity to you. I mean, we can basically cleave this off. I don't know if you can see my cursor. I'm wiggling it around. I can cleave this off. I can ionize that, and then this can be a free radical. And then this takes on very different properties. So this can be the exposure medium, just like you would have in ZEP. Okay, so this has got a mass. This has got a mass. So the probability of this colliding with this, because it's a lot bigger, is going to be a lot higher. And then this will essentially strike out a lot of secondary electrons. And the beauty is the secondary electrons don't really go anywhere because they don't have enough energy to do that. And essentially, I need to talk to you about this as well. So this is a benzenoic acid, so you can put metals on this side. This is incredibly inert. Okay, so our friends at HRL, so Guy DeRoses and my friends at HRL, I gave them this molecule to expose, okay? And I told them that the exposure dosage is going to be wild. What I mean by wild is like 100,000 microcoulombs per centimeter squared. And the exposure dosage for this was 120,000. Why do they use it? Because they've got legislation in Southern California that only allowed them to use certain solvents. But my friends there were exposing this at like 250,000 and then gave up because they couldn't overexpose it. And what's going on here is you've got electrons in this benzene ring here, or this aromatic. And what's happening is the electrons are coming down here, and then this is just spinning until it goes to ground. So the electron energies across this, here, and here is much higher than at this point, okay? So you need a lot more energy in order to break this, okay? Now, what's the trade-off? The trade-off is this is super high resolution, okay? I mean, you can get like 5 nanometer half pitch with this quite easily. This is incredibly robust. It's very inert, and it's great, apart from the dose is wild. Now, the way that we can counteract the dose is we can use this isonicotinic acid, and we have this nitrogen, and this nitrogen just makes the reactivity a lot, because electrons like nitrogens, especially if they're like amine technologies, which I'll talk to you in the next slide. But essentially, this brings the affinity, the electron energy a lot lower. So this is able to get smashed and destroyed a lot quicker than this, okay? So essentially, this is some of the ligands that I work with, or I have worked with, apart from this. And these two I've never worked with, but all the rest, Guy, myself, and my PhD students have worked with all of these, okay? All right, now we were talking about passive ligand design. Now we're going to talk about active ligand designs. So essentially, you can see if I go back to the last slide, you can see that the numbers on this was 120,000 per million, and we've got 50,000, okay? And so you can see that this is like almost half of that, and that's why I mean it could be up to 50% of the exposure. Now, if I put a metal on here, I can increase this, depending on what my exposure medium is. Oh, sorry, wrong way. Right, so we're talking about active ligand design now. So we're going to talk about alkenes to start with, and essentially we can see this molecule here. Okay, so it's basically a double bond. So the electron, there's no bond on this side apart from this hydrogen. Okay, so if this is bonded into the ligand, then the electron can come out here, smash this, and then it can release a secondary electron, and it can basically carry on. So you're kind of getting 2 for the price of 1. Okay. So you're getting 2 electrons for the price of 1, and essentially this is how it kind of works, really. So you've got your electrons, smashes this, and it kicks 1 out. Okay, so a good example of, I'm going to move myself once again. A good example of these alkenes is an acrylic acid. So I don't know if you were at 3 Beams last year. Devon at Georgia Tech, he was talking about polyacrylic acid, which is a very good negative tone. Rubbish, absolute rubbish resolution. They're talking about a micron, but the dose is like 1, maybe 2 microcoulomb centimeter squared, depending on how you hit it, what current you used. But yeah, it's extremely high. Okay, so you can see that if I've got a metal attached to this, I can essentially generate secondary electrons, and it follows this, and then this basically kicks out, and it can either bond to another one, which is right next to here, so you can call it a cross-link. It can happen, but what tends to happen is that, where's my cursor? There we go. So what happens is that this basically starts to decompose. Okay, so these start to decompose, if you can imagine a metal here, so you end up with a metal oxide that's no longer soluble in your solvent, and that's the reason why they work. So essentially, if my energies of my secondary electrons is too high, I need more. I need a longer carbon chain, which we can do here, and we have the same kind of mechanism. All right, so you can just extend these. Okay, so there's something else. So we have an amine technology. So amines are brilliant. So they help me out a lot, because you can probably tell that all my exposure dosage are massive. Because what we're doing, essentially, we're making metal oxides or semiconductors. And metal oxides, metal fluoride oxides and whatnot, metal sulfides, they're not soluble in organic solvents when you come to develop them, or when you come to sublime them back off, they're not sublimable. Okay, they'll evaporate if you put enough heat through them,